In this lecture, we are going to see the topic Class P and Class NP problems. Usually, the problems can be categorized into two ways. One is a hard problem or easy problem. So, what is easy problem and what is hard problem? Sometimes the dividing line between easy and hard problem is a simple one. For example, it is very easy to find the shortest path in a graph from the particular node x to another node y, but it is very difficult to find the longest path in the same graph from the node x to y. So the first one is easy problem and second one is hard problem, but the same problem for both category, but it is very easy to find the shortest path, but it is very difficult or hard to find the longest path in the same problem or in the same graph. Or otherwise this problem can be viewed in another way, that is yes or no problem. So for a same graph or a same problem, there is something simple path between the node x to y, and each and every edge having some weight, and capital M is nothing but the overall weight of the particular graph. So if the weight of that node x to y is less than or equal to the total weight, then it is very easy to find the path from x to y. But it is very difficult if the single weight of the path from x to y is greater than the overall weight, then it is very difficult to find the path of the particular graph. So this is the difference between easy and hard problem. So the first problem, that is easy problem, which can be solved in a particular stipulated time, that is polynomial time. But for the second one, hard problem, having some algorithm, known algorithm, for the second one hard problem, it should take some exponential time to solve the problem. So both problems have to give the solution, but for the first problem can be solved in polynomial time, but for the second one it takes some exponential time to solve the given problem. Considering the decision problem, we all know what is decision problem. If a problem can be easily decided with either yes or no, then the problem is said to be decision problem. Consider the example for decision problem is knapsack problem, 0 or 1 knapsack problem. So for this problem, we can easily take the decision with either yes or no by using some known algorithm x. So this is decision problem. From this hard and easy problem, we can derive the classes P and class NP problem. So what is P? What is class P? That is polynomial time. So here the problem in class P, the problem can be solved in polynomial time. So those problems which can be decided in polynomial time, that problem is called as class NP, and also the problems in class P are very efficient. So what is NP? That is non-deterministic polynomial time. It is not non-polynomial time. It is also here also the problems in NP can be solved in polynomial time, but it is non-deterministic Turing machine. That's why the name is given for NP is non-deterministic polynomial time. It is P is polynomial time, NP is non-deterministic polynomial time. So for the problems in NP, it takes some exponential time to solve the given problem, right? So it can be, the meaning is it cannot be solved in polynomial time. The meaning of NP is it can be solved in polynomial time, but it takes some exponential time to solve the problem in non-deterministic Turing machine. For P, class P, it is used in deterministic Turing machine, but here is non-deterministic Turing machine. So what is the difference between deterministic Turing machine and non-deterministic Turing machine is nothing but in deterministic Turing machine the solution is determined, which means we can't guess any solution, either this or that, because in deterministic means the solution is determined one, which gives the correct solution or optimized solution for deterministic Turing machine. But non-deterministic means the solution is not determined, so we can assume or guess any solution, any possible solution for the corresponding problem. So that is non-deterministic Turing machine. So the class NP are those problems that can be tested or verified in polynomial time. So this is class P. So problems can be solved in polynomial time on deterministic Turing machine, which means the solution is determined one. So what is NP? Here P belongs to NP. The class P belongs to NP only, because every problem in P has a solution, has also solution in NP, but it is not reverse, which means NP does not belongs to P, because there is no solution there is no solution for a problem in NP. Also it don't have solution in P, but every problem in P has a solution in NP also. So for NP is nothing but the problems can be solved in polynomial time on a non-deterministic Turing machine. So P belongs to NP only. So already we saw that the decision problem or solvable problem, unsolvable problem can be solved in a way like reduction method. Reduction means here the undecidable problem can be reduced to another problem by using some known algorithm. So here also the same concept. Here the algorithm, known algorithm capital A can be reduced to another algorithm capital B. So here the solution is either yes or no. These are some of the examples for P and NP. So this is the first column is the example for NP problem, and the second column is example problem for P. So the classes P and NP. Class P and deterministic Turing machine for a given decision problem X. If there exists the polynomial time deterministic Turing machine that solves the given problem X, then that problem belongs to the P. P is nothing but class P. So there is a polynomial time algorithm to solve the given problem capital P. This is class P. So it is obvious P belongs to NP, right? So a decision problem in P does not need guess solution, because the class P is in deterministic Turing machine. Already I said there is no time for guessing the solution, because the correct solution can be computed in polynomial time. So the problem in class B can be solved in polynomial time, which means the problem in P having the correct solution which can be computed in class P. So there is no need of guess solution for the problem in class P, but we can guess the solution for the problem in NP, because NP is non-deterministic Turing machine. So the same example problem 0, 1 abstract problem is an example for decision problem. So here the main question is the class P is equal to class NP. Is the both problem same or not? The answer is no, because P belongs to NP only, but NP does not belongs to P. So that's why P is not equal to NP and NP is not equal to P, but P belongs to NP, which means the problem in P can be solved in the problem in NP. So what is optimization problem and what is decision problem? In the word sense, decision problem means we can give the solution as either yes or no, which means we can easily decide whether the problem give the solution either yes or no. That is decision problem. So what is optimization problem? So for optimization problem, we can find the solution with the best value. That is optimization problem. What is algorithmic complexity and problem complexity? Algorithmic complexity is nothing but it is a measure of how it is difficult to perform the particular computation, that is which is specific to the each and individual algorithm. So complexity of the particular problem or task means it takes the lowest order value of the growth of complexity, which means consider the example. The problem for searching an ordered list has at most log time complexity, log base n time complexity. And what is computational complexity? It deals with classifying the problems by how the problem should be solved. So the same one, class P problems that are solvable or decidable in polynomial time. So these are the examples for polynomial time, that is order of n2, order of n power n cube, order of 1 and order of n log n. So what is the examples of non-polynomial time? That is order of 2 power n, order of n power n and order of n factorial. So these are the example order growth value of complexity of non-polynomial time. And what is tractable and what is intractable problems? So the problems in P are called as tractable problem because problems in P can be give the solution, correct solution, so that is tractable. Problems not in P are intractable. So problems not in P means the corresponding problem don't give the correct solution, which means that is unsolvable or intractable. So example for unsolvable problem already we saw in unit 5 beginning, that is halting problem or halting decision problem. So this is that is the famous example for unsolvable or undecidable problem. We saw one theorem for halting problem. So example for intractable problem, Hamiltonian circuit and traveling salesman problem. Both are the examples for intractable problem. So non-deterministic Turing machine and NP problem or NP class NP. So it can two-stage procedure. The first one is guessing stage and second one is verification stage. So guessing stage here we are using that because it is non-deterministic Turing machine. So it is the solution is non-determined. So we can guess the solution, guess all possibilities solution for the corresponding problem. So the first stage we have to guess the possibility of the certain solution. In the second stage we can verify. So the first one is non-deterministic because we can guess only. There is lot of possibility of the possibility solution for the problem. So that is non-deterministic. Second verification stage is deterministic because after guessing the correct value we can verify that the particular corresponding value is correct or not. So that verification stage is determined only. So here in NP class, verification stage is polynomial. So what is class NP? NP consists of the problems that can be solved by NP algorithms, which means it should be verifiable in polynomial time, but it is guessable in non-polynomial time. So here the notable point is NP does not mean that non-polynomial. In the first slide itself I told NP means non-deterministic polynomial time, that is not non-polynomial time, because the problems in both P and NP are solvable only in polynomial time, but for P that is a deterministic Turing machine, for NP that is non-deterministic Turing machine. So that the name is given for NP is non-deterministic polynomial time, that is not non-polynomial time. So the same question here is P is equal to NP. The answer is not, because P belongs to NP, but NP does not belongs to P. So the same one, the undecidable problem or unsolvable problem can be solved by the reduction method, because reduction is the best way for the given problem to solve in an easy manner. Here we say that the problem A is easier than problem B. So we can write it as A belongs to A less than or equal to B. Here if we can solve the problem A using an algorithm, the same algorithm should be used to solve the problem B, because A can be reduced to another problem B. So one algorithm to be used for the problem A, the same one should be used for another problem B also. The important point here is the input is given for A should also pass to the second problem capital B. So what is polynomial reduction? For a given two problems A and B, we say that A is polynomially reducible to B. So it can be rewrite as A belongs to capital B with polynomial reducible. Here also the same one. Here the problem A can be reduced to another problem B. So the solution is either yes or no. Here it uses a polynomial time reduction algorithm to transform A into B, and it is run by known polynomial time algorithm for B. Use the answer for B as the answer for A. and using the same input for A to be used for the problem B also. So these are all about what is class P and what is class NP problems. Now we will see one example problem for class P and class NP problem. So you can you should know the concept about class P and class NP. So the problem can be solved in polynomial time of deterministic Turing machine, that is class P. So what is class NP? The problem can be solved in polynomial time and it also takes some exponential time with non-deterministic Turing machine. So P is polynomial time, NP is non-deterministic polynomial time, it is not non-polynomial time. So first we will see the example problem for class P problem, which means here in this algorithm or in this problem give the solution in polynomial time. So this is an example for class P. The example is Kruskal's algorithm. So the problem with efficient solutions are all coming under the category of class P. Here the example problem is MWST, that is minimum weight spanning tree, is an example for class P problem, which means this problem gives the solution in polynomial time. So what is spanning tree or what is minimum weight spanning tree? So in spanning tree is a subset of edges such that here all the nodes are connected through edge where there are no cycles, right? It is a tree and in the tree having edges of all nodes and without the formation of cycles. So what is minimum weight spanning tree? It has the least possible total edge weight of all spanning tree, that is a minimum weight spanning tree. So N represents node, E represents edge. Each and every edge has some weight represented in some integer value. So a well-known greedy algorithm is there called Kruskal's algorithm for finding MWST, minimum weight spanning tree. So a spanning tree is nothing but it is a tree with some edges of all nodes without cycles. There are no cycles in the formation of tree, and minimum weight spanning tree has the least possible edge weight of all spanning tree. So there is an algorithm for minimum weight spanning tree to find the optimal solution. So in the first step we have to maintain the connected component for each node, that is the first step. So in the second step we have to sort this edge of the node in ascending order of their weight, because each and every edge having some weight as in integer value. So in the second step we have to assemble all the weight of the particular edge in some ascending order. So in third step we have to select the lowest weight edge. Last step we have to repeat the step 3 until all edges of the tree have to be visited at least once. So this is an algorithm for minimum weight spanning tree. This is an example to find minimum weight spanning tree. So there are 4 edges in this graph, in this tree or graph, 1, 2, 3, 4, and each and every edge having some weight. 1, 2, 3 having 10 weight, 1, 2, 2 having 12, 2, 2, 3 having 18, 3, 2, 4 having 13, 2, 2, 4 having 20, and 1, 2, 4 having 15, right? So in the first step we have to assemble the weight of each and every edge in an ascending order. So the integer number 10, 12, 13, 15, 18, 20, this is an ascending order, so we have to assemble like this. So W is equal to, W means weight of that each and every individual edge. Ascending order, we have to assemble in ascending order. So 10, 12, 13, 15, 18, 20. So these are the all weight of the edges. So number of nodes are 4. So N is equal to 4. In the second step, in the third step we have to select the lowest weight edge, right? So the lowest weight edge is 10. So 10 is a weight edge. So what is the node to be used for connecting the weight edge 10? That is 1, 3. So we have to draw like this, 1, 2, 3 having 10, because we have to select the lowest edge weight. After 10 the lowest weight is 12. So we have to draw in the second step 1 to 2 the second node having the second lowest weight, that is 12. After that the lowest weight is 13. After 12 the lowest weight is 13. So that coming from 3 to 4. So in the next step we have to draw from 3 to 4, that is the weight of 13. So the step is over because in the last line you can clearly see that the step 3 can be repeated until all edges have to be visited. So there are four edges, 4 nodes, 1 2 3 4. Here 4 nodes have been completed by the weight 10 12 13. So the total weight is 10 plus 12 plus 13. The result is 35. So this is an example for class NP. So here this problem can give the solution 35, optimum solution 35 in a polynomial time. Within a stipulated time we can solve the problem and give the solution 35. So this is an example for class P problem. Next we will see the example problem for class NP. So for class NP the example problem is traveling salesman problem. So here this problem can be solved in polynomial time with non-deterministic Turing machine. So what is traveling salesman problem? Consider the graph. G is equal to V comma E. V is vertex and E is edges. So connecting two vertex V1 comma V2. Edges means we have to connect two vertex V1 comma V2. So a salesperson has to visit each vertex, each node exactly once and returns to its starting point with the minimum distance. That is traveling salesman problem. So a problem give the solution like a person has to visit each vertex or node exactly once and returns to the starting point with the minimum distance. That is traveling salesman problem. So this is an example problem. There are 4 nodes 1 2 3 4 having the same weight like in the previous problem. So here we can easily solve the problem. We will start with from the first node, first vertex 1. So it goes from 1 to 2 and then 2 to 4 and then 4 to 3, then 3 to 1, right? So here 1 2 3 4 there are 4 nodes and here the 4 nodes have to be visited at once, which means it covers it forms cycle 1 2 4 3 1. It starts from 1 and also ending with 1 and it forms a cycle. So this is traveling salesman problem. So consider the weight 15. 1 to 2 is 15, 2 to 4 is 20, 4 to 3 is 18, 3 to 1 is 10. So 15 plus 20 plus 18 plus 10 is equal to 63. So here the solution for this traveling salesman problem is 63, right? But for class P problem in Kruskal's algorithm we can find the minimum weight of that particular spanning tree without cycle formation, but here we can form the circle in traveling salesman problem. So this is an example for class NP. So in this lecture we saw about what is P problem, what is class NP and what is polynomial, and saw some example for P and NP problems.